But for a physicist, we usually don't look at the temperature, but how the energy propagates from one object to another.
Good afternoon, sir. My name is
Good
Rayan
afternoon.
Hinto, and I'm a BS Physics student. So, first, sir, I'd like to ask you some questions related to your background and experience, especially in the field of thermodynamics and more specifically Newton's law of cooling. We're hoping to gain a deeper understanding of how this law works and how it can be applied to practical situations.
So I've studied thermodynamics in the undergrad years. So actually in physics, thermodynamics is not a standalone subject. We use the what we call statistical mechanics. So we're interested in the propagation of phase space instead of the usual space-time trajectories that are being used by engineers. I guess it is indeed useful or significant in thermodynamics, but as a physicist, we usually don't use this Newton's law of cooling, but we use an equivalent principle, which is the second law of thermodynamics. Newton's laws of cooling is derivative with respect to time, so it's a rate of flowing of temperature. So all I can say is when the phase of matter is the same, then we can use this Newton's law of cooling. But if we are going to have to consider the phase transitions of matter, then we are going to use the what's this? Yes, the second law of thermodynamics. So we have this what we call self-healing materials. So these self-healing materials, there are some self-healing materials that operates on the change of temperature. So if we are going to, if we know how temperature varies with respect to time, then we can predict how fast the healing of these self-healing materials will proceed. I think in the storage of the medicine, there's a label there, must not exceed 30 degrees Celsius.
Yes.
There are some bottles containing that.
Yes.
Okay. So that's because certain medicine may at certain temperature will exhibit a chemical change. Okay, and also the container might, of course, it might do some expansion.
Yes.
So compromising the medicine. We have actually three kinds of formulation in physics: the Newtonian, Hamiltonian, and Lagrangian. So the difference is that the Newtonian is actually, it will give you the exact perception of the physics behind everything. Now, Lagrangian and Hamiltonian will give you the energy and how phase-space configuration works. But the mathematical rigor or the mathematical needed for the other two, which is Lagrangian and Hamiltonian, might be quite hard. But the Newton is virtually impossible to solve in certain settings. So the difficulty now is, although the Newton's formulations can give you the exact what is happening or the exact physics of the object in a more sensible way, the math will take a lot of time and maybe or even impossible to solve. So that's the challenge of using Newton's methods.
Okay, thank you, sir. From the discussion, you seem to have a strong background in thermodynamics and heat transfer. And the insight you shared about Newton's law of cooling and its applications have been very helpful for our research. You've shared valuable input on Newton's law of cooling and how it can be applied to medical storage applications. So your contributions will really help guide our study. I believe I have all the information I need for now. Would it be alright if I reach out to you again in case we have follow-up questions?
Okay, it's fine.
Thanks again for your time. We're looking forward to sharing what we've learned with the rest of the class. Thank you po.
Thank you.
Thank you, sir.